Hello everyone and welcome to Physics 6 lab activity on Archimedes Principle. Hopefully you have that printed out off your data sheet for Archimedes Principle. What we're going to do today is use Archimedes Principle to measure the specific gravity of certain materials. Now what the heck is specific gravity? Well, you know what density is, right? Density of an object or material is the mass divided by its volume. Well, what specific gravity is, it's the density of an object compared with water. So specific gravity, just say Sg, equals the density of any material divided by the density of water. In other words, it's just how many times denser is it than water. If something has a specific gravity of 2, it means its density is twice the density of water, and so forth. Well, we'd like to be able to measure the specific gravity of aluminum and some other materials. We can do that using Archimedes' principle in a very clever way. Since density is mass per volume, if we take the mass per volume of an object divided by the mass per volume of water, that would give us the specific gravity. But if we could somehow use an equal volume of water as the object, this is the object, this is the water, if their volumes were somehow made to be equal, they would cancel out, and the specific gravity of an object would just be the mass of the object over the mass of the water, if their volumes were equal. We can use Archimedes' principle to do that. The specific gravity of a material is the mass of the material divided by the mass of an equal volume of water. Okay, so how are we going to do that? Well, remember what Archimedes' principle says. It says if you measure the mass of an object, actually they talk about weight, but we're going to use mass because the G and the mg cancels out in the end. If you measure a mass of an object in air, using maybe a spring scale or a balance or whatever, and then if you measure it in water or any fluid, it's going to weigh a little bit less. The reading on the scale is going to be less because it's experiencing a buoyancy force pushing up on it. Now what Archimedes' principle says is that if we could, when we put the object in the water that gets displaced, if we could catch that in an overflow can, the water that gets displaced, the weight of that water is equal to the buoyancy force. In other words, the amount of mass that the object seems to lose is equal to the weight of the water it displaces. That's Archimedes' principle. Buoyancy force equals the mass of the water displaced. So, notice that the mass of the water displaced is equal in volume. The volume of that water is equal to the volume of the object because it's the object that displaced it. The object displaces the same amount of volume as its own volume. So here we have a piece of water whose volume is the same as the mass of the object that displaced it. Okay, well, what's the definition of buoyancy force? It's the mass in air divided by the mass in the, minus the mass in the water. It's the amount of mass lost. The buoyancy force equals the mass in air minus the mass in water. So how much it weighs in the air, you weigh it in the water, how much mass it loses, that's the buoyancy force. So, if we can measure the mass of something in the air, remember the specific gravity equals the mass of an object, that's that, divided by the mass of water of equal volume. But the water displaced has equal volume, and the water displaced is the buoyancy force. That's Archimedes' principle. The buoyancy force equals the mass of the water displaced. Well, the buoyancy force is just the mass in air minus the mass in water. So mass in air minus mass in water. writing H2O for that. That'll give us a specific gravity. Now, if you look at the formula on your calculation page, where it describes your calculations, the first thing we're calculating is the specific gravity of an aluminum cylinder. And the formula is just the mass of the aluminum in air divided by the mass in air minus the mass in water. Can you see that this denominator is just the buoyancy force, which is equal to the mass of water displaced? So we've got the mass of the aluminum divided effectively by the mass of the water of equal volume, and that gives us specific gravity. So let's do that. Let's do that right now with an aluminum cylinder. I'm going to measure the mass in the air with a balance. I'm hanging it by a string so that we can submerge it in the water. So let's get a reading of this mass of the aluminum in the air. Let's see what this thing, what its mass is. It's an aluminum cylinder. It's almost 70, it's going to be 60. That's pretty close, 69.6. So what we're going to do is write on your data page, right here where it says the mass of the aluminum cylinder in air. What did I say? 69.6. So we're just going to write 69.6 grams plus or minus 0.1 grams. Okay, what are we going to do now? We're going to submerge it in water. We're going to submerge the aluminum in water. And notice what happens to the balance here. As soon as we put it in the water, it's lighter now, or it has apparent weight that's less, apparent mass that's less. Let's see how much lighter it is. It's only 40-something now. It's lost quite a bit of apparent mass. Didn't really lose the mass, of course. It's just what's showing up on the scale because of the water. And this is giving us 45.6 grams. So the mass in water is just 45.6 grams plus or minus 0.1 grams. Immediately we can use this data to calculate the specific gravity of aluminum by using our formula that we already saw. The mass of aluminum in air divided by the mass in air minus the mass in water, because the mass in air minus the mass in water is the buoyancy force, and the buoyancy force is just the water displaced, the mass of the water displaced. Who said that? Who said the buoyancy force is equal to the mass of the water displaced? Archimedes. Okay. So far so good. We've managed to use Archimedes' principle to measure the mass, or actually the specific gravity, of aluminum. But what if we wanted to measure the specific gravity of a liquid using this same method? Well, let's replace the water with rubbing alcohol. So if we suspend the object in rubbing alcohol and take the mass in air minus the mass in alcohol, mass in air minus the mass in alcohol, well, that's the buoyancy force, which is the mass of the alcohol displaced. But we want to compare that with water. We want to compare that with the mass of the object in air minus the mass in water. Well, we already did this one. We took the mass of the aluminum in air minus the mass of the aluminum in water. We did that previously. Now we're taking the mass in air minus the mass in alcohol. If we divide one by the other, we're dividing a mass of alcohol with a mass of water that has equal volumes. Because according to Archimedes' principle, this, being the buoyancy force, equals the water displaced. This, for alcohol, is the buoyancy force in alcohol, which is the mass of the alcohol displaced. But they both have the same volume because they're both displaced by the same aluminum cylinder. So that's going to give us the specific gravity. I know this is a little complicated and we're going kind of fast, but you can rewind and play it over again and think about it until you really feel you understand why this formula gives us the specific gravity of alcohol. So what we're going to do is actually do that. I'm going to dump the water out and replace it with alcohol. But I'm going to try to carefully wipe out the beaker so that we don't contaminate the alcohol. We're going to try to serve it. So now I'm going to fill the beaker with rubbing alcohol, 70% concentration. That ought to do it. Place the beaker on the lab jack. So now we've already got the mass of the aluminum in air and the mass of the aluminum in water. Now let's measure the mass of the aluminum in the alcohol. It's going to be different. Should it be more or less than in water? Well, it's displacing the same volume of alcohol, but alcohol is lighter than water. So I'm saying the weight is probably going to be, it's going to have less buoyancy force. It should be greater than it was in water. So let's measure the weight in alcohol. Looks like it's going to be 40 something. .7. So now we can record that value where it says mass in alcohol. Just want to be sure I get it right. 48.7. 48.7 plus or minus 0.1 grams. So now we have the mass of the aluminum in alcohol. So immediately we could calculate the specific gravity of the alcohol. This is the specific gravity of the alcohol. It's just the mass of the aluminum in air minus the mass in alcohol divided by the mass in air minus the mass in water. So the calculation, the measurements and calculations are super simple. But understanding how Archimedes' principle ties in here is the key. It's what really needs to be understood. Okay, so what else can we do? We've measured the specific gravity of a solid, aluminum. we've measured the specific gravity of a liquid, rubbing alcohol. But what if we wanted to measure the specific gravity of a piece of wood? Now we've got a different problem because wood floats. And I'm just going to take a moment to pour this alcohol back in this bottle so we don't lose it. Probably contaminated a little bit with alcohol. It's all right. So now we want to measure the specific gravity of a piece of wood. So how are we going to do that? We're going to hang a lead mass to the wood. That's going to allow us to get it to sink. But how do we take care of the buoyancy force in this case? Okay, it's a little bit complicated. What we do, we're going to measure the mass of the wood in air. See, the specific gravity of the wood is equal to the mass in air divided by the buoyancy force when it's in the water. Because the buoyancy force is the mass of the wood, of the water displaced by the wood, which is the mass of an equal amount of water. Okay, so we're going to measure the mass of the wood in air. Then, what we're going to do, we're going to attach to the wood, this is wood, the lead sinker, and we're going to measure the mass of the wood in air, mass of wood in air, plus the mass of the lead. I'm using Pb for lead, the chemical symbol for lead, in water. Now this might be a little hard for you to read. Let's see if I can zoom in on that a little bit. Okay, so there's the mass of the wood in air and the sinker in the water. Okay, that will give us a number. Then we're going to submerge both in the water together. The wood and the lead in the water, mass of the wood and lead in water. So what's the difference between these two pictures? What's the difference between this mass and this mass? The only difference is that you have the wood in the air and the wood in the water. So what's the difference between the wood in air and wood in water? It's the buoyancy force on the wood. That's what we want, the buoyancy force on the wood. So if we take the mass in air, that's the mass of the wood, and divide by the mass of the wood in air and the lead in water, minus the mass of the wood plus lead in water, that'll give us the specific gravity of the wood. I'm going to bring the camera a little closer so you can see what I wrote a little bit better. Actually, this is exactly what's on your data page. So we got the mass in air of the wood divided by the mass of the wood in air, the lead in the water, minus the mass of the wood and the lead in the water. The only difference between those two is the upward force on the wood when you put it in the water. That's the buoyancy force on the wood, which Archimedes says is equal to the weight of the water displaced. So if you look on your data page, well, let's do the measurement first. we're going to measure the mass of the wood by itself in air. Pretty light. So let's do this. Oh, it's very light. Not even 10 grams. So the mass of the wood in air is just 7.7 grams. Mass of the wood cylinder by itself in the air, 7.7 grams. Now we're going to attach the lead sinker to the wood. And we're going to measure with the wood in air and the lead in the water. That's what we have right there. You see the wood is in the air, the lead is in the water. Now there are some hooks involved. The hooks are different materials, so that's a possible source of measurement error. We're going to ignore that. So now we get a much higher reading because we've got some lead involved here. Less than 200 grams. 220 something. Okay, 222.6. So, the combination of wood and sinker with only the sinker submerged in water, and you can see it's 122.6. $122.6 grams. That's the wood in air and the sinker in the water. What's going to happen when we put the wood in too? When you raise the water so the wood is lowered in the water, what's going to happen to our weight? Of course, it's going to be less because there's a buoyancy force. Now, the only difference between the measurement before and this one is now there's a buoyancy force on the wood. And that's equal to the weight of the water displaced, which is an equal volume of the wood. So now it's going to weigh less. Okay, we've got 110, 112, 112.9. So here we have the wood and sinker together, both in the water, 112.9. Grams. So now we have all the data that we need. The only thing you need to do is calculate the specific gravity of the wood, and I will be giving you on our Canvas website the actual densities of the alcohol in the wood, so that you have them to compare to calculate the measurement error and the percent difference. Actually, be the percent error. So it says here to calculate the percent error of the results. We're not doing the last part. The last part says to do the specific gravity of an unknown material. For the sake of brevity of the videotape, we're not going to do that part. So this is all we're going to do. You have all the information you need to do the calculations. In your conclusion and discussion, be sure to talk about the purpose of each procedure, describe how you accomplish that procedure, describe and evaluate the results, talk about your percent error, whether it's good or bad, and so forth, and make a complete, comprehensive list of sources of measurement error, of which there are many. So, good luck with your report. Let me know if you have any questions. And that's it for this particular presentation.